Good day, my fellow scholars. My name is Ujah Oliver. I'm here to present my work titled Analyzing the Effect of Spark Plasma Sintering Process Parameters on the Tribological Properties of Aluminium Carbon Nanotube Niobium Composite. This work was co-authored by Professor A.P.I. Popoola, Professor O.M. Popoola, Professor V.S. Aigbodion, and Mr. Uyor, all in the Department of Chemical, Metallurgical and Materials Engineering, Tshwane University of Technology, Pretoria, South Africa. In the conference titled Sustainable Engineering and Industrial Technology, holding in University of Nigeria, Nsukka, online, this day, 6th to 11th July 2020. This work will be presented following this outline from the introduction and motivation through the conclusion. Introduction and motivation. Research shows that spark plasma sintering is a very popular powder metallurgy fabrication technique because of the following attributes attached to it. It conserves energy due to low sintering temperature of operation. It suppresses grain growth due to its high heating and cooling rates. It improves material properties as it ensures full densification of the material developed. It saves time as the sintering is completed within 5 to 10 minutes. It is cost effective since it utilizes very low energy and a very short time. It vaporizes impurities by the use of the vaporization power of the plasma formed. Full densification by allowing micro and macro diffusion of particles. Now, why did we choose aluminium as our base material in this work? Aluminium has found many applications in a variety of places because of the following attributes. Aluminium alloy has low density, it has low ductility, it has high ductility, it has high corrosion resistance and high electrical conductivity. However, the application of aluminium in its monolithic form is undermined by the following factors. Aluminium has low strength, it has low wear resistance, and it has very high coefficient of thermal expansion. Hence, this is the reason why aluminium was always reinforced with some other particles. And in this work, aluminium was reinforced with carbon nanotube and niobium. The reason for the choice of these reinforcing phases include the following. Carbon nanotube has a high modulus of elasticity of up to 1 terapascal. It has high strength of up to 30 gigapascal. It has very low density. Carbon nanotube has high thermal conductivity of up to 3000 watts per meter Kelvin. Carbon nanotube produces carbon film, which aids in wear and corrosion resistances. Niobium, in other words, produces niobium oxide that protects material from wear and corrosion. Niobium is, in short, a superconductor and is equally a good fraction toughening agent. For these reasons and others, carbon nanotube and niobium were chosen to reinforce aluminium so that it will be able to put into a very good usage. Let's take a brief look at materials produced with aluminium composites. 1. Aluminium aircraft wing. B. Engine blocks. C. Transmission conductor. D. Cable tapes. We can see that aluminium, when combined with the appropriate reinforcing phases be able to work perfectly well in this variety of places. That is what the major reason why aluminum is always reinforced, so that it will bring out the best property of aluminum combined with the properties of the reinforcing phases. Objective of the study. The main objective of this study is to determine the effect of spark plasma sintering parameters on tribological properties of aluminum carbon nanotube niobium composite. This main objective was achieved with the following sub-objectives: microstructural characterization of the powders as well as the sintered samples, tribological testing of the sintered samples, and finally, statistical analysis of the result using Taguchi design of experiment and analysis of variance, in short form called ANOVA. Methodology. This work was divided into three major parts, namely pre-sintering operations, sintering operations, and post-sintering operations. In post-sintering operation, we had weighing of the powder, mixing of the powder, and characterization of the powder. In sintering operation, it involved sintering of the material, of the powder material, following strictly the design of experiment that is shown in table 1. In post-sintering operation, activities involved microstructural characterization, tribology testing, and statistical analysis of the tribological result. Methodology continues. Table 1 shows Taguchi design of experiment for spark plasma sintering operation. 1A shows the raw result of the DOE, design of experiment, whereby first parameters were randomized into 3 levels to give 9 sets of experiment. The B shows the interpretation of the design of experiment, whereby parameters of sintering temperature, pressure, dwell time, and heating rate were randomized at 3 levels to give 9 sets of samples. The sintering was strictly done using this table, so that at the end of the day, the material developed was characterized to determine the best parameter that gave us the best tribological property. Results and discussion. Figure 3 shows transmission electron microscopic images of ARPS received powders of A, aluminium, B, carbon nanotube, C, niobium, D, agitated carbon nanotube. From 3A we see that the microstructure, the grain of aluminium is spherical in shape, as well as the grains of niobium, shown in figure 3C. Spherical grains, according to research, is very good at improving the densification of the material. It equally improves the comprehensive strength of the material, and equally good at suppressing grain growth. In 3C, we can see that carbon nanotube possess convoluted tubules held tightly together by van der Waals forces. This phenomenon makes it hard to disperse on the aluminum matrix. That is why before the mixture, the material, the nanotube was agitated, as can be seen in figure 3D, which made it very easier for dispersion of the reinforcing phase. Figure 4 shows the same images of the sintered samples. Here we can see that there is a uniform dispersion of the reinforcing phases, and then some of the microstructure has some pores, and subsequently in the subsequent slide, we will see which sample has the best microstructure. This shows the same EDS of the sintered sample, where we can see that niobium, aluminium, carbon, and silicon are seen in the sintered samples, then, which tells us that there were no material lost as a result of the sintering. This is the result of the coefficient of friction of the sintered samples. Here we can see they are the material with the least coefficient of friction, which is our interest, is sample 8, sintered at 630 degrees Celsius, 40 megapascal, 5 minutes, and 300 degrees Celsius per minute. There is a common trend here. The trend is that when the applied pressure increases, the coefficient of friction decreases. This is because increased force tends to increase the heat generated by the sample, which tends to soften the material and reduce the coefficient of friction. This is Taguchi analysis result of signal to noise ratio of the coefficient of friction of the samples. Here we can see that parameters of 630 degrees Celsius, pressure of 50 megapascal, dwell time of 5 minutes, heating rate of 200 degrees Celsius gave us the highest signal and the lowest noise. Hence, this is the parameter, the optimal parameter that gave us the best coefficient of friction. Table 3 shows the ANOVA result of coefficient of friction of sintered samples. From this we can see that the sintering temperature has F value of 39.05, R squared of 96.86%, where we infer that it has high significance. Pressure has a very low F value, meaning that means that it has very low, is non-significant. Dwell time is non-significant, heating rate is non-significant. But interaction between sintering temperature and pressure is very significant, with R squared or coefficient of determination of 94.53 megapascal, percentage. Interaction between sintering temperature and dwell time is equally highly significant. Interaction between sintering temperature and heating rate is equally very significant. Here, from this table, we'll be able to see that sintering temperature is a very important parameter that plays a prominent role in determining or in reducing the coefficient of friction of this material. So also the interaction between the sintering temperature and other parameters. Outside this, all other parameters are not statistically significant. In conclusion, this study, we were able to observe that spark plasma sintering of aluminium carbon niobium produced a densified composite. The sample produced with the sintering temperature of 630 degrees Celsius, pressure of 40 megapascal, dwell time of 5 minutes, heating rate of 300 degrees Celsius per minute, yielded the least coefficient of friction and best microstructure in this study. There was an agreement between Taguchi analysis and the experimental result. However, ANOVA result showed that only sintering temperature and interaction between the sintering temperature and pressure, dwell time, and heating rate were statistically significant. Hence, sintering temperature played a dominant role in reducing the coefficient of friction of the sintered composite. Finally, spark plasma sintering has proven to be a good fabrication technique that has improved the tribological property of aluminum matrix composites with optimum parameters of 630 degrees Celsius, 40 megapascal, 5 minutes, and 200 degrees Celsius per minute. Acknowledgement. The authors do hereby acknowledge the financial support of the following: Center for Energy and Electric Power, CEEP, Tshwane University of Technology, Pretoria, TUT, and also the Botswana International University of Science and Technology, BUST, who ran the tribological tests. We appreciate you all. This is the selected references. I thank you all for listening to the said conference paper number 80. Thank you.